Sorry, what? Right. So,
and then you have to multiply by 0.4 for the length on the top. You just have to divide by it on the bottom as well. And you divide by 0.04 again. And I got.
so the first thing you do is find that the lambda, right, is equal to the charge per unit length. So then you can ignore the endpoints. Now, it turns out you can actually just go ahead and use the 10, and it doesn't hurt you at all, because the 10 doesn't matter, right?
You just so much faster.
But if you find lambda as that, then you're just blowing through the same way you do the previous row. Right? You're going to pick your shape. Your shape's going to be a cylinder. Why? Because it is a cylinder, and in addition, that's symmetric, and it has electric field the same way throughout. So I'm going to go EA equals Q enclosed over E naught. I'm going to do this just to make the guy who's reading my test happy. And then the electric field is what I'm looking for. The shape is going to be an unrolled cylinder. So that's going to be 2 pi r times the length of the cylinder. It's going to equal charge enclosed, which is what the length of this doesn't really tell me what's enclosed there. Actually, does it say how long it is? Doesn't matter. It's 4 centimeters of length, but the radius is that. So 0.13 is all that matters. So I could either use the length of the cylinder here, and here it wouldn't matter, right? Because it can't matter. The length of the cardboard cylinder can't matter. But I'm going to go ahead and do it the way we're supposed to. Charge enclosed is going to be the length that's enclosed times the charge per unit length. Those lengths cancel out, and away I go. All right. 5 times 10 to the negative 7th over 2 pi. The radius of the cylinder was 0.13 times 8.85 times 10 to the negative 12th. Run through the calculator and get my electric field. B, the total electric flux through the cylinder. Now we have to do that problem in just a moment. Right, Q over L, as long as it's symmetric, right? As long as the charge is evenly distributed. My charge per unit length is just my charge divided by the length of the thing. What do we get for the answer for this?
I got something like 69,167.
That sounds like a familiar number, and I would guess it would be, so that sounds good. 7 divided by 2 divided by pi, 0.13 divided by 8.85 exponent negative 12, and I get, what'd you get?
69,167.
I'm with you. All right. Now, what's electric flux? Because this is the question that drives me crazy. I understand why they're asking it, because I want to make sure that I mention that there's something called flux and how we get to this equation, right?
Just divide that by the area.
So divide that by the area, or simply use Q enclosed over E naught, right? You can either side of the equation gives you flux, right? Yeah. So Q enclosed over E naught, or this would be my preference simply because you can go back to the original number and divide it by E naught and call it a day. Or
would that be the 0.5? No, right?
No, wait a second. Hold on. Let me double check something, because that's normally the way to do it, but let me hold on a second.
Wouldn't you just do charge per unit length multiply?
Yeah, I might have to think this through just a moment. Hold on. It says total through this cylinder. Okay, so the problem is, I think you're right. I think we'd have to do this side. Normally you could do either side. We have to do this side. Why? Because not all of my charge is enclosed anymore. Although I could chop it, right? Yeah. I could just do charge per unit length for that little length there. Right? Would that be okay? Yeah. So I could do either side of that equation, and just be aware of that. They'll ask that question simply to say, hey, what's the electric flux? And honestly, the answer should be, what is electric flux? It's not a real thing, and I'm not going to answer your question because it's a dumb one. But that's not, you're not allowed to answer that way. So you're going to have to go ahead and pick one side of the other side and solve for it. Okay? Yeah, the total number of imaginary lines traveling through this tissue paper box, this roll of toilet roll, is... Now, get snickety if you want. They shouldn't ask the question. They do.
The people who don't do it. What do we do after like Gauss's law?
We're done with the chapter.
We're done with the chapter.
Pretty much. We're gonna start calculating voltages off of it a little bit, and we'll do a little bit of that just to make sure we remember how to do that. And that will be a little bit different than the previous chapter because we'll have electric field that we modeled rather than here's a magic electric field formula use it.
What comes after like the student
Circuits.
circuits?
Yeah, we'll circuit next.
That's exciting.
We'll do resistors, capacitors, and inductors.
Are we gonna build circuits like for labs and stuff?
I would say yeah, except we'll see. The time I was just looking at the schedule to this morning, and I'm not liking what I've seen.
What if we just sped up everything? Yeah, let's like do that. Actually try it. Like
That would be great if you guys would try. That would be awesome. You did your homework. You're good. You're on it today. We're rolling.
So maybe
The imaginary shape's going to be a cylinder, obviously. Run an electric field 12 centimeters out, so my imaginary shape's going to be 12 centimeters out. I'm assuming I'm small enough from the ends, it doesn't matter. And I'm going to go EA equals Q enclosed over E naught. I'm going to make the person happy by writing this down. One of the few places where AP Central and the physics test will dock you a point simply because you didn't consider geometry. That's how you consider geometry. You write down that sentence first. The fact that you picked the right shape, you can't possibly show that you know what you're talking about. All right, E, and then A is going to be 2 pi RL, and I got lambda R over here over E naught. Now, did they give us a lambda R? Did they give us a lambda this time?
no, we have the electric field.
Well, they have the electric field, so they want to know the electric field at a point. Oh, kind of the net charge on the shell. Okay, so I'm going to be able to calculate the.
Wait, yeah, that's the element.
Yeah, I'm going to calculate. Yeah, so I can calculate. So give me electric field. I'm going to be able to calculate my 4.8, my charge per unit length, right? And that times the length of the thing is going to give me my answer for.
Just B0.
Radius would be 0.12. Get there in just a second. 0.12 equals lambda, which is what I'm solving for, and I got 8.85 times 10 to the negative 12. What do I get for lambda? Great question. Let's get a great answer. 4.8 exponent 3 times 2 times 0.12 times pi times 8.85 exponent negative 12. Boom.
I got like
3.20 times 10 to the negative 8 coulombs per meter. Agreed? Okay. Now, if that's my coulombs per meter, how do I figure out what my total charge is on the surface? Multiply the length of the tube, right? That's cylindrical shell. And it's 150 centimeters long, so I'm going to multiply by 1.5. So it's going to give me 4.80 times 10 to the negative 8 coulombs. Oh, not lambda anymore. Now it's Q enclosed. Okay, so now the next question, what's the electric field at 0.4? 0.04.
Is that
Right there.
Right in the middle, right?
It's in the middle.
That's 0 then, right?
The shape I'm going to draw is a cylinder inside this cylinder. How much charge is enclosed?
0.
0. Therefore, the electric field at that point would be
0.
0.
Nice.
All righty then. All right, let's get the lab started. Although the first part of the lab is